Alright, so today, whatever it is, we're going to be talking little trig identities. Ones that you've seen, but again, we're going to continue to look at them from a slightly different point of view. Not just something to be memorized oops, 16. Not just something to be memorized or to torture you with, but it actually makes a lot of sense. So, for instance, suppose I take this beautiful one here, which we talked about previously. Sine squared theta plus cosine squared theta equals 1. Now we mentioned that, but why is that? Well, if you look at it from a trig standpoint, from a circular trig standpoint, there's 1. This is sine of theta. This is cosine of theta. So ergo, it has to work. But it also has to work on just a regular triangle too. Okay? Because think about this for a minute. So this is let's say this is, well, that's C, sure. And this is theta, sure. And this is B, why not? And this is A, sure. So let's think about this for a minute. What is the sine of A theta rather? Well, it's A over, no, it's not. It's B over C, right? And a cosine, of course, is A over C. God, shut up, stupid dog. Morons. And of course, so when we do this, shut up. Anyway. So if we do this, if we have sine squared of theta, of course it's going to be b squared over c squared, am I right? Sure, of course you're right, Mr. True. And the cosine squared of theta is going to be a squared over c squared. Sure, why not? Well, think about this for a minute. So if you have b squared over c squared plus a squared over c squared, you really want to say that's equal to c squared, but it's not. It's c squared over c squared. In other words, what I've done here is I had a squared plus b squared is c squared. All I've done is divide everybody through by c squared. And as you know, that is the cardinal rule of algebra. Okay? Whatever thou doest to one side, thou must also doest to the other side. Now, this is one way to write the Pythagorean identity. Another way to do it is to divide everybody by cosine squared. And if you do that, you will find that you get tangent squared plus 1 equals secant squared. Okay? If you're weird, of course, and we will use this one a lot later this year, you could rewrite that as this guy. Okay, just move the 1 to the other side. Now going back to this problem up here, what if you divided everybody by sine squared? Well, you would get 1 plus cotangent squared is equal to cosecant squared. And then, of course, I don't know why that's there. And of course, you could then solve that around another way. Worthless neighbor dog. Oh, I just want to go thump him. Those three guys right there, 1, 2, 3, 1, 2, 3, are the Pythagorean identities, they're called. And of course, these guys are just different ways of writing the same thing. Also, we will use this fella somewhat as well. That is, we'll just move the cosine over. And we can do the same thing with cosine as well, right? We could make it cosine squared equals 1 minus sine squared. Okay? Well, that's great. What else can we do, Mr. Groom? Hey, I'm glad you asked. So we've been talking about these. So we know that the sine of negative x has to equal negative sine x. We know that both from the graph, right? Because it's obvious. Here's negative x and here's positive x. And oh, look, their y's are opposite to each other. But we know this because this is an odd function. And we know that the cosine of negative x is equal to the cosine of positive x because cosine is an even function, right? They have to match on both sides. That's great. So then we talked about that today. But what if we did this? What if we said, well, what if I said to you, I want to do the cosine of some angle theta plus some other angle alpha, let's say. Now I could go as nuts as that as I want to, but what I'm really saying is this. You've got some alpha angle or some theta angle here, I don't even care what it is. And you've got some other angle you're going to add to that, so some theta like so, or alpha like so. You see this? So I'm going to add this angle plus this angle, and I'm going to get some new angle. What is the cosine of this new angle? That's what we're asking about, okay? And of course it's going to be related to these guys. And the relationship is this. Now, I could derive this one. I don't think this one really is that terribly exciting to derive. So I'm not going to. I'm just going to straight up tell you that's what it is. I think your book uses A and B, but I wanted to go Greek tonight, so I'm going with it. Okay? So we're going to do this. Now notice it says if it's theta plus alpha, you're going to use a minus sign on this side. If it's theta minus alpha, you're going to use a plus sign. Okay? Now, this one here, again, you need to be comfortable with these. You do not have to memorize them, but you must be comfortable with them. Okay? So here's what happens. It's kind of fun, actually. Suppose I said to you, hey, you know, I mean, you could do some boring ones, like, for instance, back in the old days, if you wanted to do the, well, like, say, the cosine of 60, or 75, rather. Well, that's the same as the cosine of 30 plus 45, for instance, right? And you're like, ooh, 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 ooh. That means that's the same as the cosine of 30 times the cosine of 45 minus the sine of 30 times the sine of 45. Well, you're right. It is. Ooh, but the cosine of 30 is the square root of 3 over 2. This is the square root of 2 over 2. This is a half. And this is the square root of 2 over 2. And so this would be like the square root of 6 over 4 minus the square root of 2 over 4. Or if you prefer, that right there. That is the cosine of 75. On your calculator, if you typed in cosine of 75 and then you went back and typed in this, they'd be identical. Okay? But you're like, this is not the 18th century, Mr. Groom. What is the real purpose today? Well, the real purpose today is this. Suppose I wanted to know what the sine of 2x is. Well, that's the same as the sine of x plus x. Well, wait a minute. That means it's the sine of x times the cosine of x plus the sine of x times the cosine of x, which, as you can tell, is 2 sine x. This relationship is something that we use a lot in calculus, all kinds of time. It's called a double angle identity because you took x plus x, so it's twice of what it was. Oops, and I didn't finish writing it. There we go. Sorry about that. So it's 2 sine x cosine x. So whenever you see this, oftentimes that is a gross problem to deal with. This one is muy bonita, sí. Other times, this one's gross and that one's prettier. And so it's nice to be able to go both ways to simplify your life. Well, does that work for cosine? Well, of course it does. It's different, of course. But it's the cosine of x plus x. Now, by the way, this is a relationship that you need to know. But it comes from that thing up there. That's where it comes from. Mr. Groom did not make it up. Okay? So this is cosine squared x minus sine squared x. This is equal to the cosine of 2x. This is kind of a big deal. This one right here. This one can be written several different ways, though. You'll remember on the previous page that 1 minus cosine squared is equal to sine squared. Am I right? I believe I am. And so that's cosine squared x minus 1 minus cosine squared. You dig me on that? I just substitute that in there. Distribute, and you're going to get, well, it's going to be 2 cosine squareds minus 1. So this relationship is one that we need to know. So is this one. Oh, but wait. Can't we do this the other way around? We can. And so, again, if you play the same game, I'll start from the top again if you like. If you plug this in, you're going to get 1 minus sine squared minus sine squared. So you get 1 minus 2 sine squared x. So these three that are in boxes are the ones that are equal to this fella right here. Okay? And it's a pretty cool deal once you get there, and you're like, oh, that's nice. That's cool, Mr. Groom. I know. Now, we will use those frequently this year, but one of the places we'll use them the most often is when they're written like this. Oops. Suppose I know I have a function like this, and I have the cosine of 2x, but I want to get it solved for cosine of x. Because I frequently don't know what 2x is, and I don't really care. But what I'd like to do is to write it in terms of just the cosine of just plain old x. So I can solve it like this, and it's a pretty sweet deal. And so then the cosine of x, technically it's plus or minus, because that depends on what the original x value was. But it's cosine of 2x plus 1 over 2. This is one of the half angle identities. And again, they're in your book, but where they come from is, I think, kind of a nice thing to be able to see. And then, of course, well, isn't it true that the cosine of cosine of 2x is equal to 1 minus 2 sine squared? It is. So watch me play musical chairs. Right? Divide by 2, and then square root both sides. We will use these occasionally in calculus as well. So these are both half angle identities. Well, again, they're identities. That should mean something to you. Identities means they're the same. Okay, when you graph them, they will look the same. So if I bust out the old calculator here, for God's sake, yes, Des Moines. That's what I meant. Let's see what's happening in Des Moines. Alrighty then. So for instance, if I do cosine 2x, because remember that's just regular cosine but shrunken down, that's the same as taking, now by the way, in the computer you need to do parentheses, cosine x squared minus, oops, darn it, parentheses, sine x squared. Oh, they're the same. How cute is that? We can also do, let's see, the sine of x, right, like so, and then we theoretically should be able to do square root of parentheses 1, no, I need to put another parentheses in there, and then I can't remember what I was going to do. Which one was I going to do? So 1 minus cosine of 2x, 1 minus cosine of 2x divided by 2. Oh no! Why is that the case, Mr. Groom? Remember, that's a square root, so it's plus or minus, yes? So plus or minus. So the places where it's up here and it doesn't look like it matches, that's because you need to know that you need to use the negative in that part versus over here it's the positive parts. Okay? But again, identities, it's all about they mean the same thing algebraically. And we use them in today's day and age because it makes calculus a lot easier. That's the only reason. In the old days, you had to do it because your calculators, you didn't have calculators. Instead, what you did was you had to use a chart and stuff like that. And it was a little grosser to do. I'm not going to lie to you about that. Okay? That's in essence what I wanted to talk about as we go through these things. Kind of keep that in mind as you go. It's kind of fun just to think of it like that. If you see something along these lines, also, I'm going to give you one more just for fun of not an identity. By the way, we have nowhere near exhausted all the identities. Okay, there's always more identities. Okay, so don't even panic about that. Yeah, alpha, I guess. Sure, why not? And, yeah, so I don't even know. Ouch. Ouch. Okay. From that piece of information alone, just right there, can you tell me what quadrant we must be in? Okay, I didn't tell you what quadrant we're in. I'm saying, can you figure it out from there? Okay, so let's think about this for a minute. Here's my circle. Clearly not, no, it's not quadrant 1, obviously. Oh, look, the sign is positive. Now, where are signs positive? Well, since this is the sine axis, quadrant 2. But so I check myself, is tangent negative over there? You know it is? It is. So we are in quadrant 2, okay? And so that just says that alpha is somewhere between pi over 2 and pi. Okay, we're in quadrant 2. So here's my question to you. From what you know, what's the sine? Well, it's 3/5. The tangent is opposite over adjacent, so there it is. Boom. Okay, so great. So here, now watch this. This is kind of a big deal. What would the cosine of 2 alpha be? Okay? And you're like, oh, I don't know. But I do. So check it, dog. So it's like this, see? One of them, but not the only one of those trig ratios is that the cosine of 2 alpha is cosine squared minus sine squared. Well, what is the sine of alpha? Well, the sine of alpha is 3/5. And the cosine is, well, it's 4/5, right? Technically it's negative 4/5, but you're squaring it anyways. And so what you'll end up with is 16/25 minus 9/25, which is 7/25. Okay? And that is the cosine of 2 alpha. Now, I know what you're thinking. Mr. Groom, can you get out a calculator? And could you show us, or could you prove it to us, that that's true, like using some real angles and so forth? For instance, by the way, you'll notice that I am in radian mode, so radians, no big deal. So I'm going to, just for grins here, I'm going to say inverse sine of 3/5, diamond enter. And you see that comes out to be 0.64. And I'm going to do this in degrees just so maybe it's a little easier for us to wrap our heads around for a moment. Oops. So 37 degrees, which I think is what I said today when we were in class. I said, or, well, you know, this is today, tomorrow, whatever. So we're saying this is basically 37 degrees down here. You with me on this? Okay. So 2 alpha would be 74 degrees. So the cosine of 2 times 37 would be equal to 74 degrees, right? Basically, I rounded it a little bit. But watch me here. I'm not going to round it. So watch me go times 2. So it's 73.73, right? Now let's take the cosine of that fella. Let's see what we get. Why, it's 0.28, Mr. Groom. It's 0.28. Geez, I wonder what 7/25 is as a decimal. Oh, no, you did. Yeah, it is. It's true. So we're going to see some of that. Here's a question for you. What would, now again, pretend you don't even need to know that, okay? But check this out. What would the sine, okay, of negative alpha be? And you're like, wait a minute. The sine of negative alpha is negative the sine of alpha. True? In other words, it's going to be negative 3/5. Let's do another one. Now this one I'm not going to check at the angle because I just don't care. I just don't care. I don't care anymore. Theta. Suppose I tell you that the tangent, no, not tangent, the secant of theta is 5 seconds. And the sine of theta is... Sorry, I'm doing math in my head. I think. So think with me, people. Secant is cosine. Yes? The cosine, you see, is positive. That means we're either here or here. That's our only choices. Oh, but our sine is negative. Meaning we are down here in the quadrant numero quattro. Meaning theta lies somewhere between 3 pi over 2 and 2 pi. Okay? That's great. So if I asked you, hey, what is the... Well, let's figure out the rest of trig ratios while we're here. So 5, 2, square root of 21. Right? So, you know, for instance, you could find the tangent. Tangent is square root of 21 over 2, and so on. Positive or negative? Negative, of course, because down here, cosine and secant are positive, right? Everybody else is negative. And we could keep going like that. Suppose I wanted to find the sine of 2 theta. Now, this is fabulous, friends. Fabulous. Think with me for a moment. This is 270 degrees. You with me? This over here is what? This is 720. Well, no, what are you doing? This is 360. And I'm going to times them by 2. That's 540. Oops. And 720. Are you with me? So 2 theta then must lie between 5. Oops, that's regular theta. So 540. So 2 theta must lie between 540 and 720, right? Because it's twice as big. Well, 540 is right here. That's 360 degrees plus 180 more. And 360 plus 360 is 720. So friends, I'm telling you that 2 theta is down here. You with me on this? That means that what's its sine going to be? Its sine will end up being negative. Are you with me? Now you don't have to think about that because this formula will do all the work for you. And you're welcome, by the way. So we know that the formula is 2 sine theta cosine theta. Okay? And so, hey, 2 sine of theta was it negative square root of 21 over 5. Okay? And the cosine was 2/5, yes? And so my answer comes out to be 4 square root of 21 over 25. That thing right there is the sine of 2 theta. Now I know what some of you are thinking. Could you do the thing with the calculator again? Well, you know, I'd love to. So let's do this. Let's do inverse sine of the square root of 21 divided by 5. Oops, I forgot the negative. Notice how it came out positive because I didn't make this a negative. Oops, darn it. So it's negative 66 degrees. Are you with me on this? Negative 66 degrees. Now let's times that by 2. Okay. Now you're saying, Mr. Groom, you said that 2 theta, that's what you said, Mr. Groom. You said it was between 540 and 720. Well, technically, this is another way of saying between here and check it right there, dog. Because 0, negative 180, whee, back around the other direction. I always wanted to go on The Price is Right back when Bob Barker did it. And I always wanted to go on the Showcase Showdown and spin the wheel. However, I wanted to spin it backwards and watch his mind blow. Because you think about it. You get some little old lady on there and she barely spins it. It barely goes around one time, but it counts. You get some big stud Marine guy on there. He spins it around. It goes around 17 million times. Lands on the same spot. Did they win the same amount of money? Yeah. I would spin it backwards. Would it count? I don't know. Bob would probably try to disqualify me. But it should still work. Okay? So, check this out now. What is, I know you're waiting for it, what is the sine of negative 132? why it's that number right there. And you're like, I don't recognize that number. Sure you do. Oh, nice, huh? All right, so that pretty much takes care of section 1.4. All right, we will be doing some more next time. On Monday, Monday we'll be talking about inverse functions, and we're going to get into a little bit more about, like you saw me just use inverse sine, inverse tangent, or whatever on my calculator. We're going to get a little bit more into that on Monday. You know. And we're going to spend a little bit more time on that. So just be aware of that. So make sure that you're up through 1.4 on the homework by Monday. Come see me if you need help. And goodbye.